So you've seen the movies, right? Mad scientists, bubbling potions, maybe a crazy explosion or two. But have you ever wondered what really goes on inside a chemistry lab? Well, today we're going to pull back the curtain. We're going to look at the real tools, the real techniques that scientists use to figure out, the building blocks of our entire world. Let's dive in.
Okay, so at first glance, this might just look like a really weird kitchen, right? So much glass. But trust me, every single piece you see here has a super specific, super important job. A chemistry lab at its heart is all about one thing: taking that invisible world of atoms and molecules and making it visible. It's the place where ideas get put to the test, where brand new materials are born, and it all happens through really careful, methodical experiments.
But hold on. Before we pour a single chemical, before we even think about making a discovery, there's one topic that comes first every single time. It's the golden rule. It's absolutely non-negotiable, and that's safety. It's the foundation for everything else we're going to talk about.
And when we talk about safety, these aren't just, friendly suggestions. They are hard and fast rules. Think about it. Your lab coat and your goggles, that's basically your armor. No food or drink? Yeah, that's so you don't accidentally swallow something you really, really shouldn't. And never, ever work alone? That's just common sense, right? If something goes wrong, you need someone there to help. This is your first line of defense, and it is absolutely crucial.
Now, you've probably seen these symbols before. The best way to think of them is like a universal language for danger. It doesn't matter where you are in the world, these little pictures tell you instantly if something is, say, flammable, or corrosive, or toxic. You don't need to read a label in another language. Learning this visual shorthand, it's one of the most important things you can do to stay safe in the lab.
Okay, this next one might sound like a no-brainer, but you'd be surprised. These are the two cardinal sins of chemistry. Never, and I mean ever, taste a chemical. And never stick your nose right over a beaker and take a big whiff. The risk of getting seriously hurt or even poisoned is just way too high. It really drives home the point that safety isn't just a list you memorize for a test. It's something you have to actively practice every second you're in the lab.
All right, so now that we've got the safety rules down, we can get to the fun stuff, the tools of the trade. Let's check out the essential gear every chemist has to master to get their experiments right.
So, I've got a question for you. Take a look at all this glassware. Let's say your entire experiment depends on you measuring exactly 25.0 milliliters of a liquid. Which one of these do you reach for? It's not a trick question. The answer actually tells you a lot about how lab work is done.
Okay, so here's the deal. Not all glassware is made equal. The stuff on the left, your beakers, your graduated cylinders, they're fantastic for ballpark measurements. When about 25 mils is good enough, they're your go-to. But for the kind of precision we were just talking about, you have to use the tools on the right. We're talking pipettes, burettes, volumetric flasks. These guys are calibrated for dead-on accuracy. And honestly, picking the right tool for the job can literally be the difference between your experiment working or failing completely.
And it's not just about volume. The exact same idea applies when you're measuring mass or weight. The balance on the left, the top-loading one, that's the lab's workhorse. It's great for quick, everyday measurements. But when you need to be incredibly precise, I'm talking down to a tiny fraction of a milligram, you move over to the analytical balance on the right. See that glass box around it? That's to protect the measurement from something as small as a puff of air from you walking by. That's how sensitive it is.
And of course, we can't talk about lab tools without mentioning this icon, the Bunsen burner. It's a classic for a reason. By tweaking the air and gas, you can get this perfect, hot blue flame. And when I say hot, I mean it can get up to around 1500 degrees Celsius. That is some serious heat, and it's exactly the kind of energy you need to get a lot of chemical reactions to react.
Okay, so we've got the rules, we've got the tools, now let's see how it all comes together. We're going to walk through a couple of classic experiments to see this stuff in action.
So first up, let's imagine we need to figure out a substance's most basic recipe. In chemistry, we call this the empirical formula. Now, this doesn't tell you the total number of atoms, but it gives you the simplest ratio between them. The cake analogy is perfect here. It's like knowing your recipe needs 2 cups of flour for every 1 cup of sugar. It's the most fundamental piece of information you can have about what something's made of.
So, how do you actually find that formula in the real world? Well, let's take a classic experiment, making magnesium oxide. It starts with weighing a tiny strip of magnesium ribbon, and you better believe you're using that super precise analytical balance we talked about. Then you use the Bunsen burner to heat it up until it glows and reacts with the oxygen in the air, turning into this whitish ash. You do a few more steps to make sure it's pure, and then you weigh the final ash. Here's the cool part. The difference between the final weight and the starting weight, that's the weight of the oxygen that jumped on board. From those two numbers, you can calculate the exact ratio of magnesium atoms to oxygen atoms. Boom! You've just found its empirical formula.
All right, let's switch gears to another core technique. This one is called titration. Now here, we're not making something new. Instead, we're analyzing something to find out exactly how concentrated it is. See that long, skinny tube with the numbers on it? That's the burette we mentioned. You fill that with a solution where you know the concentration perfectly, and then you slowly, drop by drop, add it to your mystery solution in the flask below.
The whole game with titration is watching for one specific moment, the end point. You add a drop of a special chemical, called an indicator, to the flask, and you wait. You're watching for the exact moment the reaction is finished, which the indicator signals with a sudden color change. So for example, if you were testing the acid in vinegar, you'd be watching for the solution to flash from totally clear to a faint pink. The second you see that pink, you stop. You read the exact volume you added from the burette, and with a little bit of math, you can figure out the concentration of your original sample. It's so clever.
So, chemists don't always know what they're working with. Sometimes they have to put on their detective hats. Imagine someone just hands you a vial with a clear liquid in it and says, "Figure out what this is." Where do you even start? Well, you start with a process called qualitative analysis. The name gives it away. It's about the quality, not the quantity. We don't care how much is in there yet, we just want to know what is in there. And it's basically a big process of elimination, like a logic puzzle, where you use a series of chemical tests to figure out what specific ions, those are charged particles, are floating around in your mystery sample.
Let's say you're hunting for negatively charged ions, which are called anions. You'd follow a kind of flowchart. Step 1. Add some barium ions. Did a solid form? Yes or no? If yes, you go to the next step. Add some acid. Did the solid dissolve? Every answer, yes or no, takes you down a different path and eliminates possibilities. You keep going until you get to a final, confirmatory test, like adding a special chemical called a reagent that makes a yellow solid appear. And if that happens, you know for sure you've found phosphate. It's just pure step-by-step chemical detective work.
And sometimes the clues you're looking for are just beautiful. Check this out. This is the famous brown ring test. You have to carefully layer different chemicals in the test tube. And if you do it right, this perfect brown ring forms right where the layers meet. There's no mistaking it. If you see that ring, it is a 100% positive sign that you have nitrate ions in your sample. It's just a fantastic example of a clear visual clue that solves a piece of the mystery.
So we've seen how chemists can be detectives, right? Figuring out unknowns step by step. But let's zoom out for a second. Why does any of this matter? Beyond just these specific experiments, what's the big picture here?
There's a line in one of the lab manuals we looked at that really nails it. It says the lab is perfectly designed for learning. And that's so true. It's not just a place to get the right answer for a homework problem. It's where all those abstract ideas from a textbook suddenly become real. They become things you can actually see and touch and measure.
And really, when you boil it all down, the skills you pick up in a chem lab are so much bigger than just chemistry. It's really a boot camp for paying close attention to detail, for learning how to observe things carefully, and for solving problems in a logical, step-by-step way. And those skills, they're the building blocks for pretty much any scientific discovery, in any field you can imagine.
Because that's what a chemistry lab really is, right? It's an amazing toolkit for making the invisible visible. It's how we understand what's in our food, or if our water is clean, or just what the world is made of. So I'll leave you with this question. If you had access to this toolkit, if you could make something invisible suddenly visible, what mystery would you want to solve?